Hello, you've made it. We're almost home free. The very last section we care about is probability. Yay! So, probability, if you've probably thought about it before, like if you flip a coin, what are the chances of getting heads? Well, you have a 1 out of 2 chance of getting heads because there's one head and there are two sides of the coin. Or, if you roll a single die, a die or a dice, whatever, it has 6 sides. It has either one of the numbers between 1 and 6 on it. So if I said, oh, what's the probability that if I roll a die, I get a 3? Well, that's only one choice out of 6 possibilities, so I have a 1 in 6 chance of getting that. So, if you've thought about stuff like that, you've already been doing probability in your head before. But that's kind of the basics of it. But theoretical probability, we call it. Theoretical probability is determined by noting all the possible outcomes. So, for example, if you roll a die, there are 6 sides. So there are 6 possible outcomes. And then determine how likely the given outcome is. Expressed mathematically, it looks like, so we always write it as a fraction. The numerator is the number of favorable outcomes. So for example, if you wanted to roll a 3, there's only one way to get that. So it'd be like a 1 over, the total number of outcomes if you roll a die are 6. So something like that. So if you want to roll a 3 on a 6-sided die, then the probability would be 1 out of 6 or 1/6 as a fraction. That's really all we'll need in the beginning of this section, but then I think it might get more complicated later. But just for now, think of it that way. How many, the numerator is how many ways there to get what you want. The denominator is how many total outcomes are there. So let's see, this first one, I think we're gonna use that fraction to figure out our probability, but we're gonna get the numbers within the fraction from this little table here. So the first part of this asks, what's the probability that a woman aged 40 to 50 has a positive mammogram? So the probability of a positive mammogram, this is usually how you write it, P and then parentheses, whatever you want to happen. Well, of course you don't want someone to have a positive mammogram, but you know what I mean. That's what we're looking for. It's okay. The numerator is the number of ways to get that outcome. So the number of ways to get a positive mammogram. I'm just going to write MAM period. And then the denominator always is the total number of outcomes. So I just have to look in that table and think about it. So, let's see, positive mammogram. Okay. Looks like the way this table is set up, okay, there are 100,000 women that were surveyed here. So I think what's going on is the denominator is going to be 100,000 because one of these things happened to them. They had a negative mammogram and they either did have breast cancer or they did not, or they had a positive mammogram and they did have breast cancer or they did not. Something like that, but there are 100,000 women total. So that's the denominator, 100,000 women total. Okay. And then the numerator would be the number of ways that there were a positive mammogram. So where was that? That would be these. Oh, looks like both of these guys added together because the top row is talking about positive mammograms. Well, either they did have breast cancer or they did not. But in this particular guy, they didn't specify. So I got to add those together. There's like 720 because they all had a positive mammogram, but also the ones that did not have breast cancer, 6,944 of them did have a positive mammogram. So it's kind of those put together because both of those had the outcome we were looking for, a positive mammogram. Let me see, I have to add those together. 6,944. Looks like 7,664 over 100,000. And, that's a good answer, but a lot of times they're going to want you to reduce. So I would try to reduce. Well, at least I know the numerator and denominator are divisible by 2. Actually, you know what? I think they're both divisible by 4. So let me see. I'm going to divide by 4. 7,664 divided by 4 is 956. Or sorry, 958. And then the denominator, of course, divided by 4 is 25,000. You know what? I think we can divide by 2 again. Oh my god, is this ever going to end? 958 divided by 2. 479. So it reduced a little more. 125 0.00. There we go. So that would be your chances of, well, based on this information, if you're between 40 and 50, the chances of getting a positive mammogram are 479 out of 12,500. And that, if you want to put it in perspective, you can make that a decimal. So make it a decimal. 479 divided by 12,500. I got about 0.03832. So that, if you want, you can think of that as the decimal form of a percent. So I'm going to move that decimal over twice. So it looks like it's about 3.8% chance, I guess, that you can think of it. That kind of puts things in perspective more if you make it a decimal. But I think what they want is a fraction. So, technically I'm going to leave my answer as a fraction, but just in case I want to wrap my mind around this problem, it'd be like 3.8% chance. Okay, and then specifically now they're saying, among women with positive mammograms, find the probability of having breast cancer. Okay, so we want to know what's the probability of breast cancer if you had a positive mammogram, I guess. Mammogram. Okay. So it's a number of ways to have, well, man, this is a bummer problem. It's bumming me out. Number of ways to have breast cancer if you had a positive mammogram, because that's what they describe. Why I'm having a hard time writing just the letters M-A-M. I don't know what the hell. Mammogram. Where are we? Here we are. Mammogram. Divided by the total number of outcomes. But they said we're talking about only positive mammograms, so it's like that would be the number of positive mammograms. Mammograms. So right now we're not even interested in the negative mammograms. Where are those? This crap right here, we're not even looking at this. Don't even look at the bottom row. We're only interested in the top row. So how many ways are there to, let's see, for women to have breast cancer, given that they have a positive mammogram? That'd be exactly this number here. Because that's in the column of breast cancer and it's in the row of positive mammogram. So for sure the numerator is 720. The denominator is the total number of ways you can have a positive mammogram, basically. So that'd be these two added together. 720 plus 6944. 720 plus 6944. Because both of those groups of women had positive mammograms. So that was the total number of women that had a positive mammogram. Let's see, what is that? 720 plus... We already did that, huh? Hello. 720 over 7664. Let me see. Does that reduce by 4? 7664. It does. Okay, so the denominator divided by 4 is 1916. 720 divided by 4 is 180. Okay, looking at that, I can see that those numbers are both even again. So I should probably be able to divide that. 180 divided by 2 is 90. 1916 divided by 2. Oh, man. Is 958, but those are both again even, so I should be able to divide by 2. Oh, my God. This is probably the worst part of probability, is just trying to reduce the freaking fraction. So it's 45 over, actually, I forgot the denominator is the same as we got before. 479. There we go. And that's what they want, but if you, like I said before, if you want to put that in perspective, divide it out. 49 divided by 479 is about 0.09394 or so. Oops, 5, sorry. But if you move that decimal to the right twice, that's about 9.4%. So you have so that means if you had a positive mammogram, you have a 9.4% chance of having breast cancer. Why do they always come up with the most bummer problems? Always. Oh well. Sorry, I kind of moved all our work into the next problem, but oh well. This one's kind of a bummer too. Well, not really. Never mind. I thought it was something else. This says the table below shows distribution by marital status and gender. Oh no, this isn't a bummer. Of the 242 million Americans age 18 or older, use the table to find the probabilities. Okay. The first one we're looking for. If one person is randomly selected from the population described in the table, find the probability to the nearest hundredth that the person is divorced. Okay, so it sounds like, first of all, when they say to the nearest hundredth, they want us to make it a decimal and round it. Round. Because they said to the nearest hundredth. If they don't specify rounding or whatever, then I just keep it a fraction, because that's usually what they want. But okay, one person, so we want probability of what now? That the person is divorced. A person is divorced, okay. So just the basic theoretical probability is a fraction where the numerator is the number of ways to get what you want. The number of, I guess, people that are divorced. And then the denominator is the total number of outcomes, the total number of people we're talking about. But it just looks like they're not specifying us, like they're not saying out of the men or out of the women. They're just saying out of the population. So the denominator should be the total number of people. All right, let me look at the table now. How many people are divorced? Where are we? It looks like there's a couple numbers there that we want to add together because the table we have male and female are kind of split apart. We have 10 males that are divorced, well, 10 million, whatever. 14 million females that are divorced. So it's 10 plus 14 equals 24 divorced. So total number of divorced would be 24. That'll be the numerator. And then the denominator is the total number of people. But you know what? I could actually, if I wanted to, I could take all the numbers in the table and add them together. But they already said in the beginning there are 242 million Americans total that we're talking about here. So I already know that we're going to be adding these numbers, and we should get 242. So it should be 24 out of 242. Let me see here, 242. And how does that reduce? Does 242, is it divisible by 4? No. I think the only thing you can do is reduce this by 2. 12 and 121. You know, so I'm reducing it by 2. But you know what? Actually, I think these are both divisible by 3 now. That's 4 over, let's see, 121 divided by 3 is... Oh, no, never mind. I guess that's it. Sorry. I was thinking of something else. So 12 out of 121 chance, but they said they want it rounded to the nearest hundredth. So I'm going to put that in my calculator. 12 divided by 121 would be 0.0, and they want us to round it to the nearest hundredth. But it looks like 991735554. The hundredth place is here, so this 9 would actually round this 9 up to a 10, becoming 0.10. So that's how they want it, but if they wanted it to, as a percentage, you'd move that decimal point over twice, so it's about 10% of the population is divorced. Interesting, okay. But yeah, I think because they said round to the nearest hundredth, I would just leave it as this decimal. Because they didn't say, and you know, if they said write your answer as a percent, then I would write it as 10%, but they just wanted the decimal, I think. Okay, and then the last part of this example, they want to know, among those who are divorced, find the probability of selecting a woman. Okay, so it looks like the denominator is the total number, but they're saying only out of those who are divorced. So the number of divorced people is what we're looking for here as our total people. But the numerator is what they want to specify, a woman. Okay, so the number of divorced women. There we go. So let me look back at my table and see, let's see. I guess we already figured out over here that there were 24 total divorced. So that'll be my denominator at least. I know that. But the number of divorced women, okay, where was that? Well, female is this row. And then this highlighted column, it has divorce. So I must want where they intersect, the 14. 14 divorced women, well, I think it's 14 million, huh? So it looks like 14 out of 24, which reduces to 7 out of 12. And I think, did they want... Well, this one they didn't say where to round, so I might leave it as a fraction. But in case they said, oh, round your answer to the nearest hundredth, like in the last one, if I put it in my calculator, I get 0.5833, and the 3's go on and on. But if they want me to round it to the nearest hundredth, this 3 would not round the 8 up to a 9, so it would just stay 0.58. But that would be if they wanted us to round it, but they didn't say that in this part, so I'm just going to leave it as 7/12. All right. We'll do a little bit more. I like these better because I don't have to go looking at a table for a bunch of numbers. This is just, think about it. So a die is rolled. Now find the probability of getting a number greater than 4. Okay, so if I want the probability of getting a number, well, I don't know, maybe this is kind of picky, but I'm going to say rolling a number greater than 4. Somehow that seems more specific to the problem. Rolling a number greater than 4. Okay, that would be the total number of ways that I can get what I want. Number of ways to get a number greater than 4. Oh, I don't know. There's probably a better way to phrase that. I'm just going to say, how about numbers greater than 4? There you go. Like on a die, how many numbers are there greater than 4? Numbers greater than 4. Okay, that's what we want. Out of the total possible outcomes, total possible outcomes. All right. Well, on a die, you know, you have all, there's, now if you can't picture what I'm talking about, I don't know. It's like a cube. One side has a 1. There's like a 1 little dot. Another side has a 2. Another side has a 3. And then the 3 sides that you're not seeing have a 4, 5, 6. So it looks like there are 6 outcomes. You can either get a 1, 2, 3, 4, 5, or 6. But now I want to know how many numbers are greater than 4. Well, the outcomes are 1, 2, 3, 4, 5, and 6. Out of those, there are only 2 of them that are greater than 4. So it's 2 out of 6 probability, or 1/3. So I have a 1 out of 3 chance of getting a number greater than 4. That's because 2 out of the 6 numbers on a die are greater than 4. Now let's try this next one. A die is rolled. Find the probability of getting a 4. So let's see. So instead of saying a number greater than 4, what if I want a 4 exactly? I have rolling a 4. Okay, that would be the number of ways to roll a 4. Ways to roll a 4 over the total number of outcomes. So okay, that would be, how many ways are there to roll a 4? Well, there's only one, because you're either going to get a 1, 2, 3, 4, 5, or 6. There's only one outcome where I get a 4, but there are 6 total outcomes. So the probability would be 1 out of 6. And then let's see, I think these next ones are going to be very complicated. I gotta really put my thinking cap on. These are the lottery. I don't know if you've ever played the lottery. Oh my god, it's so complicated. It's like, I think it's, you choose 5 numbers out of, shoot, what does it say? In this case, they're saying out of 69 numbers, and then you have to choose 1 number out of 26. You have to get all of them right. Holy crap. But let's see, okay, in Powerball, a minimum award of $50,000 is given to a player who correctly matches 4 of the 5 numbers drawn from 69 white balls and 1 number drawn from 26 red Powerballs. They want us to find the probability of winning this consolation prize. Express the answer as a fraction. Okay, well, the total number of combinations, I guess, because you're looking for the probability of winning, I guess, of this minimum award. Minimum award. Okay, it's the number of ways to get that minimum award. Number of ways to get the minimum award over the total number of outcomes. So I think what they're doing right now is they're calculating the denominator. The denominator, the total number of outcomes is, it's like, okay, the first part of this is how many ways are there to choose the 5 numbers out of the 69? How many ways can we choose the 5 of 69 white balls, or whatever they're called? And then you have choosing 1 of the 26 for the, what they call it, the Powerball number. Yeah, you want to choose 1 out of 26. So it's kind of like, this is really like 26, choose 1. But as we've seen, we had a rule in the previous section where 26, choose 1 is just 26. So they're filling everything in. Okay, we want to choose 5 out of 69. That gives us this formula for 5 choose 69 times 26 choose 1, but we know that's just 26. And then they multiplied it all out. Of course, you can use a calculator. They didn't use one, but you can. No problem. And you end up getting 292,201,338. So that's just the denominator of our answer. So we know so our probability is going to be something over 292,201,338. The numerator, though, is we want to find the ways to get the minimum award, which means you're getting 4 of the 5 right. So that you're asking yourself now, okay, let me see. The number of selections that match 4 of the 5 white balls, I guess it's like the number of ways to choose 4 of 5 balls. So it's like, I only want to get 4 of the 5 right. So here it is. That's how I choose the 4 out of 5 that I want right. And then any one of the 64 non-selected white balls. Because this will be how many ways are there to get 1 wrong. So it's like, yeah, this is how many, the ways to get 4 correct 4 correct. And then this guy's the ways to get one wrong, because they're saying we don't want to win the Powerball award, the big award. We want to win the minimum award where one's wrong and the other 4 are right. Ways to get one wrong, incorrect. So just so you know, this is way too complicated of a problem for our exams, for sure. This you might see again in the future in a more complicated, a higher level math class, but right now you will not see this on an exam. Just maybe the homework, so don't worry about it too much. I don't want you to stress. And then this is you have to get the mega ball right. There's only one way to guess the correct mega ball. I mean, you do it or you don't. So there's only one way to get it right. The correct mega ball number. All right, and if you multiply those together, those 3 values, whatever 5 choose 4 is times 64 choose 1, and then times 1, you're going to get this numerator, 320. So this is your probability here, but if you reduce it a little bit, you get this guy. Holy crap. That's some complicated stuff. So we'll try to duplicate that just so we kind of have an idea, but I don't know. Don't feel like you have to reproduce this on an exam. This is way too difficult. Okay, it says in Mega Millions, a player wins the jackpot by matching all 5 numbers drawn from 56 white balls and matching the number on the gold mega ball. There are 46 gold balls. Okay. What is the probability of winning the jackpot? Okay, that's what I want. Probability of winning the jackpot. Okay. That would be, if I write it as a fraction, that's the number of ways to win, okay, over the total number of outcomes. Okay. And then, maybe just to be similar to what they were doing, I'll calculate the denominator first. Denominator, total number of outcomes. Okay, total number of outcomes. So, okay, the Mega Millions, the lottery is very complicated. You have to choose, what was it? You have to choose 5 of 56 balls. And I think I don't think the order matters. Just like they showed in this one. Where is it? I'm going to highlight it. Order should not matter because notice they use combinations. If it was a permutation, that would mean order matters. So I want to choose the 5 out of 56. I'm choosing, first of all, I'm choosing 5 of 56 white balls. Okay. Which means I'm using this combination thing. I'm going to choose 5 out of 56. So that's one portion of it. But then also there's a golden number or mega number, whatever the hell. Oh my God, why is the lottery so complicated? You have to match the number on the mega gold ball. There are 46 gold balls. Okay, so you want to choose out of 46, you want to choose the one correct. So you want to choose 1 out of the 46. Choose 1 of 46 gold balls. So this should be the total number of outcomes, kind of like what they did over here. So then I can just use a calculator. I don't have to do it the long way like they did. They use the formula for the n choose k or n choose r, whatever. I don't have time for that crap, You guys don't either. This guy, that 56 choose 5 is, well, I'll use the same color just so I don't confuse myself. Holy crap. 3819,816. Holy moly. Did I do that right? 3819,816. Yeah, holy crap. And then 46 choose 1 is just going to be 46. I know that because that was one of our little rules from the previous section. And let me multiply those together. I get, holy moly, 1,757,11536. Oh my gosh. So there's 175 million and change ways that you could choose your numbers for the lottery. But remember, this is a probability, so I know that my answer should be something over that, because that was what we calculated to be the denominator. What was it? Dang it, I lost it. It was 175,711,536. Holy moly. All right, that was the denominator. Now I want to calculate the numerator. All right, so I want to calculate the number of ways to choose. I have to choose the 5 winners of the 56, and then I have to choose ways to choose the winning, what would they call it? Mega ball? I always forget why. Yeah, mega ball, whatever. Gold ball. Oh my god, who gives a crap? Oh. This one will be a little different than the last one because in the last one, let's see. Well, in the last one we didn't want to win the big prize. We actually wanted to get one wrong. We wanted to get 4 of the balls right and 1 wrong. In this case though, we want all 5 correct. So let's see, I'm gonna maybe highlight just to show what's going on. Let's see. The number of ways to choose 5 of the winners. So let's see, I guess it's more like I'm choosing 5 out of 5. Choose the 5 winners of the 5. You know, they already have the winning numbers in their minds, I guess. How do I choose 5 of those 5? I'm choosing 5 out of 5 winners. That's kind of the idea here. Choose 5 of the 5 winners. I'm not really choosing out of 56 because I want to win. So this is asking how many ways are there to win. Times, okay, and then what else do I need to do? I want to make sure that what is it? I choose the gold ball, but that means I want to choose 1 of 1 gold balls. So even though earlier they said how many balls were there to choose from, I forgot. There were 46 balls to choose from, but if I want to win, I have to choose that 1 winner out of the 1. And the numerator ends up being a 1 times a 1, which is a 1. 1 out of 175,711,536. Which actually the numerator makes some sort of sense because there's only one way to win. You have to get all 5 of the white balls right and the gold number right. That's only one possible outcome. There's no other way to win. You have to do that. But so now that you see this probability, you have a 1 in 176 about million shot of winning. I don't know. I think you mostly see people that know probability don't play the lottery very much. Yeah. Oh my God. So that's very complicated. Don't worry too much about it. The next things we're going to cover is way more important. So, okay, the probability of an event not occurring. This is very important in probability theory. So sometimes if someone asks you to calculate, okay, what's the probability of this thing not happening? It's easier to find out what's the probability of it happening. So if you have something that's difficult to calculate, what you can do is just say, okay, well, the probability of something not happening is 1 minus the probability of it happening. So it's kind of crazy, yeah. So that's another way to phrase it, I guess. The probability of an event not occurring is 1 minus the probability of that event occurring. And you'll see people use this little formula, especially when the probability of the event actually occurring is easier to calculate than the probability of it not occurring. So I can imagine we're going to use that in this next example. Let's see, what does it say? It says, in a 190-minute NFL TV broadcast, 63 minutes are devoted to commercials. Find the probability that a minute of NFL broadcast is not devoted to commercials. Okay, because the numbers they gave us didn't talk about not devoted to commercials. So let's see, the probability of a minute not devoted to commercials, according to our formula, is 1 minus the probability of the opposite. A minute is devoted to commercials. A minute is devoted to commercials. So okay, 1 minus, and it's going to be a fraction. What's the probability it's dedicated to commercials? Well, 63 minutes are devoted to commercials out of a total of 190. So it'd be 63 out of 190 is your chance of there being a minute devoted to commercials. But if I want it to be not devoted to commercials, I just take that and subtract it from 1, which would mean I need to get a common denominator. So I'll multiply this guy by 190 over 190. So it's 190 over 190 minus 63 over 190, which would be 127 over 190. And I think that's about it. Yeah, I don't think that reduces. So that'd be it. So you have a 127 out of 190 chance of any random minute. Let's say you only catch 1 minute of a game. Then your chances of it being a minute that's not devoted to commercials is about 66.8%. So I mean, that's not that great. you might see a commercial. And the next one, if you are dealt one card from a 52 card deck, I want to find the probability that you are not dealt a king. So the probability of not dealt a king is 1 minus the probability I am dealt a king. I'm dealt a king. Okay, well you kind of have to know a little bit about cards, but if you don't, like it says there are 52 cards in the deck, so that means there are 52 total outcomes for when I grab a card. But there are 4 kings in a deck of cards, so just in case you didn't know that. You know, if this was on a quiz or something, or an exam or something, I would try to, first of all, I try not to use cards, but if for some reason I have to use cards, I try to give you all the information you need in case you've never seen cards before. So it'll be 1 minus 4 over 52, and actually 4 over 52 reduces, to, what the hell? I'm sorry, it's 1 over 13. So you could combine that with the 1 first and then reduce, or I like to reduce first. But 1, I can find a common denominator. 1 is the same as 13 over 13. I'm going to take 13 over 13 and subtract 1 over 13. That's 12 over 13. So I have a 12 out of 13 shot, or what's that in decimal form? If I make that a percent, about 92.3% chance of not getting a king. But I think since they didn't specify round to the nearest yada yada, I think they're going to want the fraction. So I just keep it as a fraction. All right. That's the first idea. Now we have some formulas. So now we're getting into more kind of complicated probabilities. So we're going to talk about probabilities with of one event happening or another event happening. And then also with the and. So it's pretty complicated. So if you want an event to, this is where you have 2 events. So it's, let's say you want event A or event B to happen. So this is kind of like on the left here, this little formula, it's kind of like you don't really care too much. Yeah, you don't really, sorry, I kind of had a break in the thing here. But yeah, if you want event A or event B to happen, it's like you don't really care too much what happens. Like it's like, just for something simple. If I was dealt a card out of a deck of 52, like we were talking about before, and I said, I'll take a king or a queen. I'd like to know what the probability is of getting a king or a queen. You're not really specific. You'll take either one. So there's a formula for that. If you want to know the probability of an event happening or another event happening, all you have to do is add those probabilities together, the individual probabilities. So it's not too bad. You add them together. So for or, yeah, keep that in mind. For or, you add the probabilities. Okay, but this other formula over here, let me try to highlight it in a different color here. We got, come on. This guy. That's the and probability, and notice you multiply the 2 probabilities. So that's pretty much the basic idea here. For or probabilities, you add them. For and, you multiply probabilities. So if we remember that, I think we'll be good for the rest of this section. All right. So let's see, in this part 4a, it says, if you roll a single 6-sided die, what is the probability of either getting a 4 or a 5? So let's see, I can write it, if I wanted to, as probability of getting a 4 or a 5. That's going to be the 2 separate probabilities added together, getting a 4 or getting a 5. So what's the chance of me getting a 4? Well, there's a 1 out of 6 chance of me getting a 4, and also a 1 out of 6 chance of me getting a 5. And I can add those together, as if they were regular fractions. 1/6 plus 1/6 is 2/6, which reduces to 1/3. So I have a 1/3 shot of getting a 4 or 5. All right, this next one says, on a roulette wheel, The ball can land with equal probability on any one of the 38 numbered slots, 2 of which are green. Find the probability of green occurring on 2 consecutive plays. So that's, I don't know, they didn't say the word and or, but it's like I want green for the first play. Does it sound, the way it sounds, does it sound like you want and or green for the second play? Is it like, oh, I'll take green for one or the other, or is, I have to have green for both? Find the probability of green occurring on 2. So they want them on both, so I think it's an and. I need green to occur on the first play and on the second play. That would mean I find the probability of it occurring on the first play, and then multiply it by probability of green occurring on the second play. But I think they're going to be the same probability because, what is it? They said there are two green out of, let's see, where'd it go? No, not there. Dang it. Sorry, let me erase that. I don't want it to be too misleading. Oh well, whatever. I want to highlight it in a different color. How about blue? 2 out of 38. 38 total possibilities. Only 2 of them have what we want. So it'd be 2 out of 38 chance of getting a green. Because yeah, there are 2 green slots out of the total of 38. But that's the same for either play. So there's a 2 out of 38 probability of getting a green on the first play and on the second play. And I think both of those reduce, right? It's 1 over 19 for either of them. And then I'll multiply those together. Of course, the numerator's 1 times 1, so it's 1. But the denominator, 19 times 19, is 361. So it looks like you don't have a very good shot of getting green on both. It's only 1 out of 361 shot. So let's try this one. Each number, 1 through 8, is written on slips of paper and placed in a hat. If one number is selected at random, find the probability that the number selected will be an odd number or, okay, there's the key, a number less than 5. So, okay, I want probability of the, one thing or another is the probability of one thing occurring plus the probability of the other thing occurring. And the things that they're asking about occurring are what? Selected will be an odd number, so I want it to be an odd number. What's that probability? And then a number less than 5. Number less than 5. Okay, well the numbers are 1 through 8, so sometimes it helps me to actually write them out. 1, 2, 3, 4, 5, 6, 7, 8. So how many of those are odd? 1, 2, 3, 4 of them. 4 out of the 8 are odd, plus how many of them are less than 5? Actually 4 of them. The first 4 are less than 5, so that's also a 4 out of 8. So you have a 4 out of 8 out of 4, plus 4 out of 8 would be 8 out of 8, or 1. Uh-oh. You know what? I'm sorry. I didn't think that they would get this complicated, but you know what? We're going to have to adjust our formula up here. I'm sorry. I thought that they were going to make this really simple, but they're not. So far we haven't had to use this because there was no overlap, but I'm going to say here we have to add a little bit extra probability of both A and B occurring. So if it's possible for both of those events to occur at the same time, then when you calculate the probability of one or the other happening, you have to actually subtract a little bit, because I think what we did in this example, I didn't think this was going to happen because I thought, I thought they were going to keep this as simple as possible because this is an intro to probability, but you have to also add probability of, you have to subtract of both of those things happening, an odd number and a number less than 5. And the reason is because when you do the addition there, so the addition we did, odd number and the number less than 5, I think we overcounted because there are numbers that are in here, they're odd numbers, but they're also less than 5. So we kind of counted some numbers twice, which is overcounting. So this is kind of balancing that out where I'm just subtracting anything I might have overcounted. So now I have to look and say, how many numbers are there that are less than 5 and odd? Let me see. Just to kind of highlight it here. This is what we're looking for. Out of this group of 1 through 8, the numbers that are odd and less than 5 are 1 and 3. So you have a 2 out of 8 chance of getting a number that's both of those things. So I can't forget about that. Subtract 2 out of 8. So I'm sorry about that. Hopefully that makes a little bit of sense that we had to do that. Because if it was just the pure addition, the probability of an odd number plus the probability of a number less than 5, that'd be way too many things, and I've overcounted because I've counted the same things twice. So yeah, I'm kind of balancing it out by subtracting anything I've overcounted. So we're really adding 4 and 4 and then subtracting 2. 4 plus 4 is 8 minus 2 is 6. So 6 out of 8 chance or 3 out of 4 chance would be my answer there. Sorry about that. Like I said, I should have looked at that ahead of time, but I thought they were making this section easier than they had to. But they weren't, of course. And then this next problem, 4D here, okay. A single die is rolled twice. Find the probability of rolling a 2 the first time and a 3 the second time. So, okay, I want probability of rolling a 2 the first time. And I think I would say it's an and a 3 the second time. Because it's not like they're saying, oh, I'll take a 2 the first time or I'll take a 3 the second time. Either way works. No, they want both of those things to happen, yeah, and. So it's going to be, I'm multiplying them together. Probability of a 2 the first time times a 3 the second time. Oh, there we go. I forgot to put probability. All right, and we're rolling a die, so it's the probability of 2 would be 1 out of 6, because there's only 1 2 on a die out of the 6 total. Same thing with the 3. There's only 1 3 on a die out of the 6 total. So you have a 1 6 times 1 6, which is 136 shot of getting a 2 and then a 3. Okay, let's see. What's next? Find the probability of a family having 4 boys in a row. So I guess that's like you want the probability of the first kid being a boy and second kid being a boy and, okay, you can see where I'm going from here. Third kid being a boy and, holy crap, we're going to fill up this whole page. Fourth kid being a boy. So far we've only seen, 2 events happening where it's I want the probability of one thing and another, or probability of one thing or another. Now there are 4, but that just means you're multiplying 4 things together. Probability of the first kid being a boy times the probability of the second kid being a boy times, the probability of the third kid. Okay, no. Third kid being a boy times the probability of the fourth kid being a boy. There were 4 kids, right? Did I get that wrong? Yeah, okay, 4 boys. All right. Well, if you think about it, it doesn't really matter if it's the first kid, second kid, third kid, fourth kid. You have a 1 out of 2 shot of having a boy, because you're either having a boy or a girl, right? So if I want a boy, it's a 1 out of 2 shot. So each of these is a half. Because, despite, I think a lot of people, they have a misconception about probability. They think, oh, let's say there's a family. They had 3 boys in a row, no girls. And then they say, oh, we're having a 4th kid. I wonder if it's a girl. I think a lot of people think, oh my God, well, this one's bound to be a girl. You already have 3 boys. But it doesn't matter what the first 3 were. Why would the first 3 affect the 4th one, What would them being a boy matter in, coming to the 4th kid? So it doesn't matter. They're all a half, no matter what happened before. So, okay, I'll multiply all the numerators together, get a 1. Multiply all the denominators together, get a 16. So you have a 1 out of 16 shot of having 4 boys instead of, 4 girls or a mix of boys and girls, whatever. So let's try this next one. They say, if you toss a fair coin 6 times, what is the probability of getting all heads? So I think that one would be really similar. You want the probability of the first being heads and the second one being heads, so it's going to be multiply. Second is heads. Yeah, I think this one and the previous one about, having 4 boys and no girls, they're really similar. You're just multiplying the probability of getting heads 6 times or the probability of having a boy 4 times in the previous one. So this one, you don't have to write all this out. This is just in case it helps. 4th being heads times the probability of the 5th being heads. Holy crap. Heads. Okay, and then there were 6. Thankfully, that's my last one. 6 being heads. Okay. There we go. And since it's a coin, there's only 2 sides, one of them being heads, right? So I have a 1 out of 2 shot here for each of these. I think this is another one where people have a misconception about probability. Like, let's say you roll a die, you flip a coin, let's say 99 times, and every time of the 99 you get heads. I think a lot of people think, oh, the next one's bound to be tails. They think the probability is better of getting tails, but, logically, why would what happened before affect what happens next? But it does kind of seem like, oh, you're bound to get tails one time. But yeah, probabilities, I don't know. Your intuition's not always right. But let's see. I think it'll be 64, huh? Because 1 times itself 6 times is 1. But 2 times itself 6 times is, 64. So you only have a 1 out of 64 shot of getting heads 6 times in a row if you were to roll a die. Flip a coin 6 times. Whew. Probability is it can get very complicated. And if you're a math major, you'll see that it gets freaking crazy complicated. Where, there are probability problems you might see if you're a math major way down the line, where you have like an infinite sum. It's adding like from k equals 1 to infinity of some kind of crazy crap, and that represents the probability of something happening. What the hell? So I think, to be honest, I think probabilities that are sort of, somewhat simple, like the ones in this section, are interesting. Especially cards for some reason, like people that gamble. What's the probability of me getting this, like a straight flush or whatever in poker? That's interesting, but as soon as you get to the ones where I have to use all kinds of crazy, ridiculous, infinite math to figure it out, it's not fun anymore, But yeah, probability is kind of interesting. But a lot of the stuff in this section is probably too complicated for exams, But especially the one about the Powerball. Don't really worry about that too much. That one, I mean, if you understand it, it's good. I think they put it in the section more to tell you, hey man, don't gamble. It's probably not in your best interest with the lottery. Probably the same thing with casinos, right? If you go to a casino and you gamble, I mean, if you look around a casino, especially in Vegas, it's a nice place, right? How do you think they afforded such a nice place? You think because they let people win? Hell no. They want your money, so they make sure they're going to win, right? So that's my friendly advice. Take it or leave it. But hopefully it made some sense. Please let me know if it doesn't make sense, and I'll try to, clear things up if that helps.